Okay, so you have in front of you guys this handout, okay, that has to do with the lab that we are going to be doing on Wednesday. Now, on Thursday and Friday, okay, on Thursday you went over the properties of compounds, and you talked about the certain things that ionic compounds always do, and the certain things that molecular compounds always do, and those are going to be important on Wednesday because on Wednesday you're going to get 11 unknown compounds. All right, they're just going to be in little glass beakers labeled A through J. K. A through K, sorry. Okay, and you're going to have to run some tests on them and figure out what they are from a list of possible identities. All right, so by the end of the lab, what you're going to have to be able to tell me is A is sodium chloride and B is copper sulfate or whatever they happen to be. All right, that's what you're going to have to be able to do by the end of the lab. So the stuff you went over on Thursday is going to be really important. Okay, on Thursday you talked about how ionic compounds are always crystalline solids at room temperature. Okay, molecular compounds are usually not crystalline solids, but there are some that are. Okay, how ionic compounds usually dissolve easily in water, where molecular compounds are less likely to dissolve easily in water, although many of them still do. Okay, ionic compounds will always conduct electricity when they are dissolved in solution. Okay, things like that. So there's some tests that you're going to have to run, and those are what you went over on Friday. Okay, when we were talking about how you design the lab, you're going to have to do a certain number of tests, and we'll review those today, and I'll show you the equipment, because I know in the podcast it said, I was just talking and I had the stuff in front of me when I recorded it, but obviously you couldn't see it because you couldn't see me. All right, so I'll show you that equipment, and you'll have some idea how it works. Okay, but just a quick review here. Okay, you've got this sheet. When you hand in a lab report, okay, or actually when you submit it to me on Google Drive, it's going to look just like this. It's going to have a problem. And that problem will be restated in your own words in the form of a question. All right, so you can't just copy it exactly as it is here, because this isn't a question. All right, in your design, you have to identify your manipulated variable, your responding variable, and your controlled variables. All right, in any experiment, the manipulated variable is the thing the experimenter is changing on purpose, okay, to find out its effect. The responding variable is the thing or things that the experimenter is actively watching for changes and measuring. The controlled variables are all the things that have to stay the same throughout the lab in order to maintain its validity. All right, so you went over a few examples of those in the podcast. I think the example I used was bulletproof glass and the different thicknesses and things like that. Okay, for this lab, and I'm going to give you some hints and tips here. Okay, you may want to write some of them down because they'll be helpful. We're running a series of tests. Are we running the same tests on every one of the unknown samples? If I've got a whole bunch of unknown samples and then I've got a series of tests, do I probably want to run all of the tests on all of the samples? Okay, so is every sample going to be treated the same? Yes. Is that manipulated, responding, or controlled? Controlled. Okay, the fact that we are doing exactly the same thing to all of the unknown materials is a controlled variable. All right, so it's important that we understand that. It has to be, because if I do one of the tests differently, then that ruins the validity of the experiment. I don't get the same results for at least one of the unknown materials, and then I can't be accurate after that. Okay, I have a whole bunch of different unknown materials. What do they represent? A responding or a manipulated variable? I'm running the same series of tests, but every time I run the tests, I'm doing it on something different. That's manipulated. Okay? The manipulated variable here, guys, is that all the samples are different, and I'm testing different ones each and every time. In the same way that on Friday when the example was bulletproof glass, okay, the thickness of the glass was the manipulated variable. I did exactly the same thing to each pane of glass. All right, but each pane of glass was different, thus they were the manipulated variable. All right, so here are different materials, our manipulated variable. What should end up different? If I run the same tests on different stuff, I should get different what? What am I watching for when I do an experiment? You usually write them down. They start with O. Observations, yeah. Should I get different results and observations each time I run the same tests on different stuff? I sure hope so, because if they all end up the same, there's no way to tell them apart. Agreed? Okay, so responding variable essentially are the results of each of the tests. There should be a different combination of results for each one. Okay, now I just gave you essentially 5 marks there. If you were smart enough to write them down, you're golden. If you didn't listen to me when I said write them down, I'm not repeating you. All right, now for our hypothesis, several times in that podcast on explaining how to make a lab report, I went over how you make a proper hypothesis. It always contains what 3 words? No? And is one of the words? If, and then. If, and then are the 3 words that every hypothesis should contain. If this is true and this is done, then this is what's going to happen. All right? So, in every hypothesis, your if part talks about your problem. Okay? If this is the solution to the problem, or if this is the answer to the problem, or if there's this relationship between these 2 things, and the following thing is done, I treat these things like this, or I mix these things together, whatever, then here is what will happen if I'm right. Okay? It always works in that fashion. All right? Now, the whole premise that this experiment operates on is that every material has different physical properties. Agreed? Okay, you talked about on Thursday that some ionic compounds have certain colors. Right? All copper-containing compounds are blue, and all nickel-containing compounds are green, and all cobalt-containing compounds are red. Okay, all of these things were things that we went over. So in there, or in that within that lesson, we should be able to figure out essentially what the physical properties for the unknown materials listed here are. Okay, so if I look at, let's say, something like cobalt-2 chloride, for an example, right? If all cobalt-containing compounds are red, and I have an unknown material that is a red crystalline solid, then it is most likely this compound. Agreed? Okay, so that's kind of the idea we're working on. Now, obviously, you're not going to have a different hypothesis for every material. That's ridiculous. All right, but your hypothesis needs to be general enough that it can cover them all. Okay, I would say that in the if part, you should probably talk about that everything has different physical properties. It's really a shame that more of you didn't write that down. Okay, the and part should talk about what you're going to do in your experiment. Maybe a quick mention of the tests that you're going to run. And the then part should tell me what you're going to be able to do as a result of that. Okay, are you going to be able to identify them all? Are they all going to have different results? Okay, things of that nature. That's what needs to be in there. Yes, but not in this lab. All right. So that's essentially the first 10 marks, of your lab report, is identifying the variables and writing out a hypothesis. Okay? Then what you're going to be working on today is the procedure. You, as a group, need to design your procedure. All right? And it can't just be 1, mix stuff, 2, write stuff down, 3, I think I'm done. Okay? That is not a good procedure. Okay? Your procedure needs to be very specific. It needs to be very detailed. You laugh, but I've seen it. Okay? And it isn't funny. Well, it's not funny, haha, it's funny, sad. Okay? So, in your procedure, you need to mention every little thing. Assume the person who is following the instructions is a total idiot. Okay? And that if you don't explain every little thing, they will blow themselves to kingdom come. Okay? That's how you write a procedure. That's how I write a procedure for you guys. I hate to say that, but okay, I write it out with every single little thing, okay, so that there's no chance, right, that it can really be screwed up along the way. So you start out with stuff that's very simple, like, acquire the necessary materials from the list. That can be your first step, okay? You can say in your next step, go and put all of the unknown materials in the depression plate or the spot plate. Okay, tell them about how much. Be that detailed. Okay, you don't want to fill it. You don't want to have like a big pile in there, because then you won't be able to add any water, right? Things like that. So you have to be very detailed, very specific. Now, you're going to be repeating the same series of tests on every single compound. Do you need to write out the same steps 11 times? No. You can say repeat steps 3 through 9 or whatever it happens to be for each unknown compound. That can save you some time. But make sure your steps 3 through 9 are really detailed. All right? Here's what you do on this step. Here's what you should be looking for. Here's what you should write down. Okay? Really, you have to tell people that much information. All right? You have to tell yourself that information. You're the one who's going to be using this procedure. And when you get into the lab, you know, things start moving really fast, you forget stuff. If you have it written down and you're reading that step by step, you won't forget, because, oh, right, I was supposed to measure temperature when I put those two things together. All right? So I got to get the thermometer and do that right now. All right, everybody follow me there? Because otherwise, you might forget. Okay, so make that procedure good and detailed. It is out of 5 marks. Okay, that procedure is out of 5 marks. The whole lab is out of 35. All right, so it's 1/7 of the mark. Okay, it's a big deal. After that, you're going to make a chart. Okay, a chart to contain all of your observations that you are going to get in the lab. That's as far as we can go until we do the lab. All right, but it's enough to keep you busy for most of class today, and I would think all of class today. All right, everybody with me so far? All right, so what I want you to do right now, because I forgot to get 2 things from the lab and bring them over here, okay, I want you to start writing out the problem in your own words in the form of a question. Okay, and then you can maybe start on your hypothesis, an if and then statement. Remembering, okay, the if part talks about the problem and physical properties. Okay, the and part talks about your experiment. You don't have to write it out in detail, just briefly describe what you're doing. Okay, the then part says what you expect to find or be able to do at the end of the experiment. Okay, so I'm going to give you a couple minutes while I grab a couple more things out of the lab to show you. Okay, and then we'll talk more about those tests that you're going to be running. Okay, and how you're going to write them up in your procedure. Okay, listen up here, guys. Quick review of the tests that you are going to need to run in your experiment. All right, so when you're writing up your procedure, all right, these are the tests that need to be included. Now, there's a couple of really important things. First off, you can't miss any of these tests. If you do, okay, you will not be able to correctly identify at least 2 or 3 of the materials. All right. The other thing is you must do them in a certain order. Otherwise, we waste a lot of material. All right. The most obvious one to do first is what we call the Observable Properties Test. And it is exactly what it sounds like. You are simply going to look at each and every material from A to K. Okay, and you're going to write down everything that you can observe directly of that material. Things as simple as color. Okay, things like its state. Okay, is it a solid? Is it a liquid? There's no gases, so you don't have to worry about that. Okay, the nature of matter. Is it crystal? Is it cloudy? Is it waxy? Is it soft? Okay. Things like that, all right? Because we already know that most of the time, if we have a crystalline solid in front of us, we're looking at what kind of compound? Ionic or molecular? If it's a crystalline solid, it's ionic. Most of the time. Obviously, there are exceptions, but most of the time, if it's a crystalline solid, okay, then it's ionic. That's going to be one of those important things when you're looking at, well, material A is, you know, it's crystalline solid, but it's white. It dissolved easily in water, and it didn't conduct electricity, and it had a pH of 7. Well, it's probably not salt then. Okay? It can't be salt because salt is ionic. Okay? And all ionic compounds conduct electricity in solution, and that material that you were just looking at didn't. All right? So, if you got a choice between salt and sugar, okay, sugar being a molecular compound, salt being ionic, that stuff is more than likely not salt, but it is in fact sugar. All right, that's kind of the process you're going to be going through. But if you don't do all of these tests, you're not going to have the data in order to do that. All right, so in that observable properties test, you're going to need the biggest space on your chart for that, okay, because you're going to have the most to write down. You're going to write down color, nature of matter. Odor test. Okay, so you're going to do the wafting test. Now, when you do the wafting test, it is not a snorting test. Okay, I do not want anyone sticking their face into the unknown solutions and going, okay, because that's going to end badly on about half of them. All right, unless you have 5 group members, you may all be dead by the time the experiment is over. All right, we don't want to be doing that. All right, because one of the materials in there, I mixed it this morning. Okay, and it's got a pH of 1. Okay. It has to, because it's the identifying feature of that material. If you snort that, you are going to have problems with your respiration from there on out, okay, as your lungs will dissolve along with your sinus cavities. So you don't want to do that. All right? Wafting test means you hold it, okay, at arm's length and gently do this. There's really only one material out of all 11 where odor is the kind of identifying feature. All right? So most of the time you're going to do this and not smell anything. Okay? That doesn't mean, if you don't smell anything, that doesn't mean get closer and sniff harder. Okay? It just means it doesn't smell. All right? The ones that smell are obvious, and you will be able to smell them by doing the proper wafting. All right? Everybody with me on that? Okay, you are also warned against taste tests. Please don't do that. All right? Many of the materials contain heavy metals, which are poisonous. Okay, some of them are obviously acidic or very basic, which is corrosive. All right, things like that. So please don't do any of that. Okay. Also on that note, you don't want to be touching too many of these things with your bare hands. Okay, so each group will have access to one of these little things. This is a scoopula. All right, because it can be both a scoop and a spatula that allows you to scrape things. So it's a scoopula. All right. So you'll use that to put all of your solid materials, okay, into your depression plate. This is a depression plate. All right. And as you heard in the podcast, it is not called the depression plate because it is sad. Okay. It's because it has depressions in it. All right. How much material do you need? Like almost none. Very, very little for these tests to work. You can't fill up this depression with material and then add water to it. It'll spill all over all the others. All right, so we don't want that. Just small amounts, enough to fill maybe about a quarter of the depression at the most. Okay, that'll be lots. Is that something you should include when you write up your procedure? Yes, when acquiring your unknown materials, please make sure to only fill the depressions 1/4 of the way full with solid materials. If the material happens to be a liquid, then you can probably go to about half. Okay, everyone with me so far? Now, the other thing we're going to do with these is there'll be lots of Sharpies in there, okay, and you will simply label each depression A, B, C, D, and then put the appropriate unknown in each one. That way you don't have to keep coming up to the front to get stuff. You can come up once, get everything, and go back to your lab table. All right, everyone follow me there? Okay, so for your observable properties then, okay, those are the things that you're going to want to write down, and anything else that you might notice that you think is important. The second test is your solubility test. The solubility test will be done with the wash bottle. Okay? It is not a squirt gun. You laugh. For some people, the first lab is the last lab they do. All right? If you horse around in my lab and you endanger the safety of others, you won't do labs. All right? So, you don't need to squeeze it very hard. People often make this mistake when they are trying to add small amounts of water to the depression plate. You also don't have to tip it. Okay? You can, but you don't have to. You just squeeze it gently, okay, and little drops of water will come out. Okay? You kind of get there, you get it going, and then little drops of water, okay, come out. You don't have to squeeze it very hard. Easy to get small amounts in there. Okay? If you squeeze it too hard, you'll shoot the stuff you have in there out, and hopefully not into anyone's face. All right, so be careful when you're doing that. Okay, just small amounts of water. Fill it, okay, till the depression and the material that's in there are, let's say, within 7/8 of the top. Okay, we don't want to go too much more than that because we still have to put in a thermometer in there during the solubility test. Okay, so you're looking for, is it dissolving? Is there a temperature change? Okay, so you got to have a thermometer in there for that test. Is there a color change? Okay, what I mean by color change is, does the water assume the color of the material? So if the crystals or whatever were blue or red, does the water turn red or blue? Because there isn't anything that's going to radically go from like yellow to green. Okay, that's not going to happen. Okay, is there any odor? Okay, when you mix the two things together, was an odor produced? There shouldn't be, okay, but it's always something to watch for. Now that you have all that stuff mixed and it's in solution, okay, now you can do the conductivity test. Okay, remember, the conductivity test is crucial. It is the only test that unequivocally tells you whether the substance you have is molecular or ionic. All ionic compounds will conduct electricity. None of the molecular ones will. Okay, now, by conduct electricity, I mean they'll have a conductivity rate of 5 or higher. Okay, if they are a poor conductor, they will be below 5 or none of the lights will go on at all. All right, now, these conductivity testers are far better than the ones we initially got because they actually tell you if they're working. When you press the button, the little on light goes on. If when you press the button, the on light does not go on, you need a new battery. Okay, so make sure you check that. So what we're doing here, guys, okay, and it looks like there was actually still stuff in this one, but okay, if we use distilled water, okay, distilled water has a very poor conductivity, right? And there was still a little bit of stuff in this depression plate, so it's reading a conductivity of 3. Okay, pure distilled water with no contaminants, 0. Pure distilled water does not conduct electricity because it's molecular. All right, everyone with me on that? Okay, if I add an ionic compound to that, let's just say we've got some salt here. Okay, if I add a little bit of ionic compound to that, and again, it doesn't take very much. Okay, we should get an increase in the conductivity rate. I put very little in there and it went from 3 to 5. Okay, you would probably have more than that in there when you do the test. All right, so it'll be obvious. If you have a molecular compound, it'll be less than 5. If you have an ionic compound, it's going to be more than 5. Some of them will go right up to the top. Okay, some of them will really conduct very, very well. Okay, so that's the reason for the conductivity test. Look for the lights, rinse in between. Okay, again, when you're writing out your procedure, your solubility test should say things like add, distilled water to the material until it is this full, and then watch for these things. While adding water, be sure the thermometer is in the depression to record any temperature changes. Okay, when you're doing the conductivity test, now take your conductivity tester and place it in the solution you made in the previous step. Okay, record the number on the chart. Then you should rinse it in between. What should you rinse it with? Tap water or distilled water? Distilled. Tap water contains ions. If you rinse it with tap water, you'll put ions in the next thing and it'll conduct electricity even if it's not supposed to. All right, so make sure you're always rinsing the conductivity tester with distilled water, and that's another thing that you should probably write in your procedure, okay, so that you remember to do it. The last test you're going to do is the pH test, okay? And so you'll have little containers of pH paper, okay? They're different shapes and sizes, but they're generally like this, and they'll have a color chart inside, okay, that tells you what color corresponds to what pH. So you take just a tiny piece off. You don't need very much, okay? So you take off, let's say maybe about this much, ½ an inch maybe, okay? Take that and simply dip it into the material, okay? You don't have to hold it in there very long. The color change is immediate, okay? Take that, compare it to your chart. I'm looking at that as a pH of 6. Okay? Record that in the chart. This piece of paper, you throw it away. All right? Everybody clear on that? Deb? Can you wait till I'm just about done here? Yeah. All right. So those are your tests. Again, make sure you write them out with great detail so that you know what you're doing when you get in there on Wednesday. Okay, and then like I said, you're going to need a chart that will have room for the observations you would acquire in each one of these tests for unknowns A through K. All right, I think I had a sample chart somewhere. Okay, so something maybe like this. All right, so sample A, physical properties, solubility. Solubility is going to be like, dissolved easily, didn't dissolve. Okay, you can kind of decide what you want to use as a qualifier on that. Conductivity is going to be a number between 1 and 10. Okay, pH is going to be a number between 1 and 14. So you don't need a lot of room for these columns, but you do need a lot of room for this one because it's the one where you're going to have the most to write. Okay. So that means this. Wednesday, when you come here, you need to be able to show me that you have this much stuff done. Okay, that you have a procedure written out, that you have a chart ready to record your observations in. Okay, you can either do that by sharing it with me on Google Drive before then, so that I can see it, or you got to have it on paper to show me. Okay, on the day of the lab, one or the other. If you don't have those things done, okay, you will not be going into the lab to do the lab. Okay, you'll be sitting in here until you have them done, and then you can come in and join us. But the pre-lab activities have to be done prior to you doing the lab. Okay, so problem, design, hypothesis, procedure, chart. Okay. Really what that means for you is you have very little to do after that in terms of homework. All right, so I'm giving you class time to do more than half of the stuff required for this lab. Right? Your responsibility after the lab will be figuring out what each thing was, conclusion, evaluation, and typing it up. Okay, are there any questions? All right, so now in groups of, let's say, 4, okay, no bigger than 4, okay, 4 is the ideal number. You can get together and you can start writing up your stuff, okay? You can come up with your problem, your hypothesis, etc. Okay, questions? Right now you're doing the pre-lab, so that's your problem, your design, your hypothesis, the procedure, and the chart. Okay? Yes. Each person, guys, that's a good question. Do we each have to have our own? The answer to that is unequivocally yes. Each of you must have your own. Each of you is handing in your own lab report. Are they going to be similar? Yeah, you're working together. Are they going to be exactly the same? No. Okay? I do not want to see 2 identical lab reports handed in from different people. Okay? P.S. I can tell if you just change the font and the spacing. All right? I was not born yesterday. People have tried that trick before. Okay? Each person needs to have theirs be at least somewhat unique. I know they're going to be similar because you're doing stuff together, and maybe your procedure is exactly the same. That I can live with. Okay? But your hypothesis, your conclusion, those kind of things, those definitely need to be unique to you. All right? Any other questions? No, they don't have to be typed for Wednesday, no. But when you hand them in, which will be after the week off, okay, they do need to be submitted to me on Google Drive, which means they'll have to be typed. Okay? Any other questions? You can go now. No, that'll have to be, because you're not submitting any paper to me. So this will, you'll have to draw a chart on your computer as part of your lab report, yes. Okay. All right. Well, let's get to it, guys. You have 45 minutes. That should be a lot of time to get a very good start on this. Okay, and this is the last class time you'll get other than whatever's left when we're done the lab on Wednesday. Oh, sorry, one other thing here. Wednesday, sorry, have a seat for a quick sec here, guys. Wednesday, proper lab safety stuff, okay? You must have shoes that cover your entire foot. That's really not a problem in the wintertime usually. Okay, it's more of a problem when people are wearing sandals and stuff, but obviously no sandals or open-topped shoes where the top of your foot is exposed. Okay, also anything that's got stuff hanging down, so you're definitely going to want to leave your headphones and stuff like that in here, because cords or drawstrings from hoodies, ladies or guys, if you got long hair, put a hair tie in your science binder, so you always have one, so you can tie it back. You don't want to lean forward into the hydrochloric acid because your hair will curl up and smell bad for a long time after. Well, yeah, it's not a nice perm though. Yeah. It's a chemical curling of your hair. It's also not all that good for you. Yeah. Okay. So keep that kind of stuff in mind, guys. Please make sure you dress appropriately. Okay. For the lab, probably not your best duds. I mean, we've got lab aprons, but they don't cover everything. Okay, and we have lab goggles. Obviously, they're not stylish by any stretch, but they work really well at keeping your eyes safe. Okay, all right, back to work. When you are doing the design portion here, make sure that you don't just identify your manipulated, responding, and controlled variables. Also make sure that you explain this is the responding variable because, this is the manipulated variable because. Okay? You have to have that reasoning in there. If you don't, you're likely to get like 2 out of 5 on your design, even if you identify them all correctly. Without the explanations, you can't get full marks. All right? So please make sure you also explain your variables.